one thing you do so well is explain the difference between ketosis and glucosis. We deep dived into this in our last episode, but I think it's fair to go to, since you've already talked about the diet, you talked about meat and carnivore, you've talked about grains, seeds, and sugars. Can you talk about the two hemispheres, as you call them, of how humans use energy?
Sure. So, Kate, what Casey's referring to when he says two hemispheres is there's only two ways that the human body can fuel its cells. One way is through glucose, and that's where the cells actually, they burn glucose, they go through the ATP cycle, and that's what produces cellular energy. And it is presumed in modern times, without, one has to completely dismiss nutritional anthropology to make this statement, but in our modern scientific times, burning glucose is considered the way you fuel cells. It's the only way. It's always been the only way. And that's a completely idiotic statement. But that's 99.9% of the world believes that. And I'm not going to get into what that actually is. Well, maybe in a bit we'll get to there. But when Casey said there's two hemispheres, it's because there's only two different ways to fuel. There's no third. And the alternative to fueling cells with glucose is to fuel the cells with predominantly fatty acids and to a lesser extent ketones. And that is what everybody's sort of the keto diet and everybody's sort of carnivore. But I'm not sure that everybody understands that the only purpose for eating that way, really, I mean, because who doesn't love the taste of a donut? Okay. The only reason that people eat keto style or carnivore style is to get into this thing called ketosis. That's where the magic happens. We eat keto style or carnivore style to get there and stay there. The magic isn't carnivore per se. The magic isn't keto per se. The magic is the physiological state of ketosis, where all 100 trillion cells of our body are rejecting glucose as an energy source and are now burning primarily fatty acids and to a lesser extent ketones. Now, when I started putting together all the information I wanted to share with people in body science, I was surprised to find that the hemisphere where your cells burn glucose for energy did not have a name. You know, what's that old adage? The last thing a fish would notice is water. Okay, well,
yeah,
the world was so entrenched in this thing that the cells burn glucose. That's what they do. They've always done. They always will do. It's the way. People were so ingrained in that that it didn't even have a name. It was just, that's normal. You have normal and ketosis, and which is totally absurd. So I actually had to find a name, and I thought the appropriate way to characterize, if burning ketones is ketosis, then burning glucose should probably be glucosis. And so I gave it that name in order that people could, because if you can't call something by its name, it becomes difficult to have a discussion about it. So ketosis was coined in 1921. So that word's been around ages, right? More than 100 years. But it was so odd to me that this other hemisphere, of which there's only two, didn't have a name. That's just crazy. And again, the more cynical side of me wonders if there aren't reasons for that, such as, I know we're going to get into in a little bit, the hepatic lipid system and the lipid system. They had no names. How do you talk about them without a name? Yeah. So the point I think I want to make when we're talking about glucosis versus ketosis, anthropologically speaking, hominids for millions of years existed from birth to death in ketosis. Glucosis was unknown to ancient man. Okay? And that only began to change, not even really with the first agricultural revolution, because that still wasn't very wide scale. Okay? That only really started to change with the second agricultural revolution, when things like grains became plentiful for the masses. And you probably know from reading history, you go back, say, into the Dark Ages, just to put a pin on the timeline. Meat was the food of royalty, and grain was the food of peasants. Okay, and it's still is today. The problem is now, over the last, I don't know, several decades, the government has convinced the American people that eating grains and sugar, that's the sign of a successful economy, and you've made it in life if you can have pasta all the time. Just absolute nonsense. Yeah.
Yeah, no, okay. So that's super well explained. Glucosis and ketosis. You've already said that the state of ketosis, we would be in that state pretty much our entire lives. If we ever exited that state into a state of glucosis, it would have been exceedingly rare. You would have to find a high amount of a carbohydrate rich food, which doesn't just like pop up everywhere. Like even if you get some fruit has changed. It's very different. The grains we use are very different than what you would have found in the past. You think about things like nuts and seeds. They were all protected. You couldn't eat whole bags of shelled almonds that you can get at the store now. It's just a completely different landscape that people don't understand. And so let's talk a little bit about the lymphatic lipid system and the hepatic lipid system and how those two things are different. Which one is the normal, natural state of delivering energy to the body, and which one is the emergency state?
Okay. Let's start with the lipid system. And the reason for that is in ketosis, that's a huge part of the healthy functioning of the body. And so what happens when we eat dietary fat? Dietary fat does not digest. Okay? It emulsifies. And so it gets into our bowels and it gets emulsified, but it can't transit the intestinal wall and go into our body. Okay? It has to be packaged, unlike carbohydrates or protein, it has to be packaged in these things called chylomicrons. Only when it's packaged in these chylomicrons, which are incredibly similar to LDL as far as their structure. Okay, they are the analogy I use, they're a delivery truck. I use the analogy in body science, a delivery truck that delivers its content throughout the body. Okay, and the primary difference between LDL and chylomicrons is chylomicrons used for structure ApoB48, and the LDL uses ApoB100. That's pretty much the only difference as far as structure is concerned. So the emulsified fat goes into these chylomicrons. They can then transit the intestinal wall. And here's the difference. This is why I call it the lymphatic lipid system. Those fats contained within those chylomicrons, they go through they're carried by the lymph fluid through the lymphatic system. They come up, they curve here, and then they come down, and they're dumped through the thoracic duct, they're dumped into our bloodstream. And then they go all through our body. And again, the delivery truck perspective, right? They have to offload these fatty acids, triglycerides, same name, two different names for the same substance, right? So they're carrying these fatty acids or triglycerides. And here's one of the things that I think is so cool about the body. The chylomicrons come along, and here's an HDL particle, here's a chylomicron particle. And as they cross, the HDL particle gives its ApoC2 to the chylomicron, okay, which was what they call a naive chylomicron. And once it receives that ApoC2, it unlocks the cargo doors. Until then, it cannot dislodge its triglycerides. It cannot offload them to the cells. So it meets an HDL, it transfers the ApoC2. Then the chylomicron goes throughout the body, hooking up with cells. Oh, there's your loading dock, hook up, here's some triglycerides, move on, here's some triglycerides. And then at the end, after the triglycerides are gone, it passes another HDL, and it gives the ApoC2 back to the HDL. It locks the doors, the cargo doors, and only when those cargo doors are locked, it doesn't possess the ApoC2, can it go back to the liver and be, I don't know what term I want to use, broken down and synthesized into something else. Okay. So that, I think, is a pretty fascinating tale. And people who are eating carnivore, as an example, they're getting probably 99% of their calories from proteins and fats. So if we just, for the sake of this illustration, we say 50-50, 50% fat, 50% protein, then 50% of their total intake, nutritional intake, gets into, energizes the cells by the process we just talked about.
Wow.
The
It's so
lymphatic
elegant.
lipid system.
Yep.
It is. It's just amazing.
Yeah, you list the pros and cons of how each one of these systems work, and this one, this delivers energy. It's in a clean way. Everything gets recycled afterwards. Your cells are happy. They burn fat for fuel. It's just it makes so much sense. So this is the preferred way. Now
Yes.
let's talk about the hepatic lipid system and how that differs from this system when we eat things like the grains and sugars that you mentioned earlier.
Okay, so for your audience who may not know, hepatic just means bearing upon or dealing with the liver. So you could call it the liver lipid, the liver lipid system if you wanted, but I think more properly the hepatic lipid system. So the interesting thing is that both of these send triglycerides out in a structure, in a lipoprotein. Okay, when it's the lymphatic lipid system, it's the chylomicron. When it's the hepatic lipid system, it starts out as VLDLs, then goes to IDLs, and then goes to LDL. Okay, which I said are very, very similar in their structure. They are all cargo vessels distributing various things: cholesterol, vitamin, water, fat-soluble vitamins, and so forth. Okay, so, but here's what happens: we eat things that are carbohydrates. Okay, we don't need to qualify what kind of carbohydrates. By the way, for your audience who may not know, every single carbohydrate, whether it's a piece of pasta, whether it's grain, a piece of bread, or whether it's some broccoli, 100% of anything that is a carbohydrate breaks down to something called a monosaccharide, which is the basic level of sugar. When it can't be glycated any further, it's a monosaccharide. Only monosaccharides can transit the intestinal wall. So no matter what a person eats, like, oh, I'm going to eat this piece of bread, or I'm going to eat this baked potato, or I'm going to have this piece of candy, whatever they stick in their mouth, it's a carbohydrate. Okay, it goes down into the intestines, and the part that transits the intestinal wall is sugar. It's a monosaccharide. Okay, so and here's an interesting thing: when it's in the intestines, it's a monosaccharide. The minute it transits the intestinal wall, now science calls it glucose, blood glucose. Okay, so same thing. Okay. So here's an interesting thing. We talked about the fact that the chylomicrons flow into the lymphatic system. Well, the monosaccharides don't do that. They go through the portal vein directly from the intestines right into the liver. Okay, and it's obviously, I think all of your listeners would know, if you eat a high carbohydrate meal, it's going to raise your blood glucose level. Okay. I'm sure you've covered that a million times in talking on various aspects of physiology. So I don't know if your audience understands that high levels of blood glucose in and of itself is toxic. And then the body's response, in order to ratchet the glucose back down to something akin to baseline, is for the pancreas to pump out insulin. Okay, insulin is toxic. Okay, now in a glucosis world, what I just said, if we were talking to some like college professor who accepts the nonsense society-wide narrative, they would say, oh, saying high glucose and high insulin are toxic is nonsense. But the studies show they are. Okay? But when you believe that glucosis is the only way to exist, kind of hard to knock it, right? It's part of your whole paradigm. So how can it be wrong? So right. What happens is when the insulin goes up, okay. Now, I think most people understand that when insulin increases, blood glucose goes down. That's the purpose of insulin in regard to blood sugar. Okay, insulin goes up, the blood sugar comes down. I think that's as far as people understand. If you ask them how does the blood sugar go down, they don't know the mechanism. Well, the mechanism is the insulin signals the liver to gather up this glucose as the blood is flowing through the liver, which is a blood organ. And then the liver extracts the excess glucose, again, trying to force that down back to baseline. Okay? And it converts the glucose to triglycerides. Okay? Now, remember, over on the lymphatic lipid system, triglycerides are good, right? We want them. But this isn't the same kind of thing. Okay? This is a conversion as an emergency mechanism to get the toxic glucose out of the blood. Okay? So then it packages up these synthesized triglycerides. They're not natural, they are synthesized. I guess they're natural in the sense that the liver does it, but the liver doesn't want to do it. The liver has to do it. Okay? Packages them up in VLDLs and spits them out into the bloodstream. Now, the cells already have triglycerides from what the lymphatic lipid system does, right? This is not an either or. The lymphatic lipid system is always operating, okay? So the triglycerides are already in the cells, okay? And then along comes these VLDLs or IDLs that have this synthesized triglycerides. And they say, hey, man, open up. We got some triglycerides. And the cells are like, dude, we are triglyceride out. We can't make any. First, you bombed us with glucose, so we had to take some glucose in and oxidize, burn that shit off, right? Now you're coming back with these synthesized triglycerides, trying to shove triglycerides into us. We're packed. We can't take any. Okay. Now, here's the thing. These lipid proteins, they get smaller as they offload their cargo. Okay? Some of them are carrying things, some carry cholesterols and other things. So as they get smaller and smaller and smaller. But what's still in there is the triglycerides because the cells don't want any. Okay? Now, or the cells are full is maybe a better way to put that. And so the LDL cannot return to the liver until those triglycerides are offloaded. Okay? So what it does is it's got to put the triglycerides somewhere. It puts it into the adipose tissue. This is most commonly understood to be like the belly fat and the love handles. There's more adipose fatty cells in the body, but the ones most people understand when they hear adipose tissue, when you see the guy at the grocery store with the gut that's hanging out over his belt, that's adipose tissue. Okay. And by the time we are, estimates vary, but we'll say approaching puberty, our body has created all the fat cells it's ever going to have. Okay? It doesn't create more fat cells. So what happens is these LDLs come along and say, we have to offload these triglycerides or we can't go back to the liver and be uptaken into the liver and broken down. We have to do something. Well, the body's emergency mechanism is here. Shove it into the adipose cells. Okay? And that's exactly what happens. Now, the thing is, in the Western diet, right, all day long, high glucose, high insulin, high glucose, high insulin, high glucose, high insulin, right? Insulin tells the adipose tissue, do not release triglycerides. So you've got the LDLs offloading their triglycerides into the adipose cells, and then the constant repetition of high insulin is telling them, lock that shit up. Do not release it. Okay? So what happens after 20 years? Obesity, right? So that's, and the problem is, we talk about, LDL in the bloodstream, that's a big thing with doctors, right? They call it the cholesterol, but it's not really the cholesterol, right? How much cholesterol is in your blood is a equation by which they estimate, and that's based on how many LDL are still floating around your blood, right? And the reason there's so many LDLs floating around the blood is two reasons. First of all those VLDLs that were spit out with converted triglycerides don't belong there in the human body. Okay, so it's flooded with things that don't belong there in the first place. And secondly, by the time they decrease in density to the point where they're the small LDL particles, they still need to go through these extra steps to find adipose cells and force the triglycerides out of themselves before they can return to the liver and be uptaken. Okay, so when somebody says, oh, you have high LDL, yeah, that's because they just keep floating around trying to find a way to get back to the liver to be uptaken and broken down and synthesized and other things or excreted as waste. I don't know if I explained that clearly. I know I rambled a bit.
Yes. No, that's perfect.
Yeah. So one, the lymphatic lipid system is completely healthy. That's the way man has existed for millions of years. The hepatic lipid system, what has always been an emergency glucose clearance system. It's meant to be, you say, ancient man, say 50,000 years ago. Perhaps the hepatic lipid system would kick in a couple times a year for a couple hours at a time. Modern Americans rely on that emergency clearance method, the hepatic lipid system, 24 hours a day, 365 days a year, and eventually they wear the body's capacity out to cope effectively, and voila, you have type 2 diabetes, you have heart disease, you have hypertension, you just, yeah, on and on.